Hi everyone, this video is about higher order derivatives. Higher order derivatives just means that we start with a function f of x, we take the derivative, d by dx, we get f prime, and then we take the derivative again. We do d by dx of that, of f, we take the derivative of f prime, and we get f, what do we call it? Well, we'll call it f double prime. What happens if we take the derivative again? We'll call it f triple prime, etc. So it's the sequential application of the derivative operation onto a function. We care about higher order derivatives because higher order derivatives can sometimes give us insight into a function or into the behavior of a model that the function describes. So if we're talking about cars on a road, the position function, let's say we call that f of t, f prime of t tells us the velocity, and then f double prime of t, the rate of the second derivative of the position, or the derivative of the velocity or rate of change of the velocity, that tells us the acceleration. Another application that's not in the science, in the physical sciences, one's in the social sciences, is in economics, something called the consumer price index. So the consumer price index works in the following way. You take a shopping basket and you throw some ground beef, some bananas, some apples. You throw some stuff in there. You go to the checkout, you find out how much it costs, and you do that every week. You put the same stuff in. It's more complicated than that. There's substitution effects. So someday you'll go look at the price of ground beef. You say, oh my God. You put it back, you get something else. You substitute in some chicken, and literally there are substitution effects built into the consumer price index. So anyways, it's more complicated than what I just described, but that gives you the rough idea of what the consumer price index is. It's trying to keep track of how much things cost, taking into consideration that we are rational, that we make reasonable decisions when prices of things go up. We might buy them less and might instead buy something else as an alternative. When we measure this consumer price index and look at changes in it, or look at the rate of change of the consumer price index, that is a measurement of something that we call inflation or deflation. So if prices are going up, we say that prices are inflating. If prices are going down, we say that prices are deflating. Different countries have slightly different measurements for inflation and have slightly different policies for dealing with inflation. This is not a class in economics, and I'm not an economist, so I've already reached the limit of what I understand. When you turn on the news and you hear about people saying that inflation is speeding up, that does not only mean that things are getting more expensive. So if let's say inflation is 2%, always 2%, that means prices are always increasing at 2%, at 2% per year, for example. If inflation is speeding up, then that means that it's going to be 2% this year, then 3% next year, and 4% next year. So that's what it means for inflation to be speeding up. It is a second derivative of the CPI to say that inflation is speeding up. It's the rate of change of the rate of change. So the inflation is already a derivative, and then the rate of change of the inflation then must be a second derivative, just like an acceleration. It's an acceleration of the change in the price of goods. The notation we have for second derivatives, we already saw it. The f prime means first derivative. It means take d by dx of f of x. F double prime means take the derivative twice. So take the derivative of f of x, that's this one here. And then when you've done that, take the derivative of that thing, take the derivative of that result. We have another notation for that. Instead of saying d by dx of f of x, we say d squared by dx squared of f of x. That just indicates that we're taking the derivative operation twice. We're squaring the operation. Like a squared means a times a. D squared by dx squared means d by dx and another d by dx. Third derivative, f triple prime, take the derivative, and take the derivative again. No surprise that the alternative notation d3 by dx3 of f of x. And the process continues for as long as you want. I'll say more about notation in a moment, but I want to go through a simple example of taking the derivative of f of x Let's go 3x x to the power of 5. And I want to find the third derivative. So it says find f triple prime of x if f of x is 3x to the power of 5. So let's take the first derivative. The 5 comes down, multiplied by the 3, we get 15x to the power of 4. Now we'll take the second derivative, f double prime. And what we do is we forget the history. We don't care that it was originally 3x to the power of 5. It doesn't matter. We're just going to take the derivative of 15x to the power of 4. So the 4 will come down, multiply by the 15. We get 60x to the power of 3. And now we're going to do it one more time. So again, I don't care about the history. I am looking at 60x to the power of 3 and taking that derivative. The 3 comes down, multiplies by the 60, 180 x to the power of 2. That would be the answer. So it's a sequence of derivative operations applied to the function. And that's just a different one with no 3 in front. Okay, so let's do the same thing for a slightly harder example, 3x squared plus the square root of x. Before we take a derivative, we have to rewrite the expression to make it ready for calculus. Square root means power 1/2, so x to the power 1/2. Now we'll take the derivative. The first part's nice. Derivative of 3x squared is just 6x. And the derivative of the second part, still the power rule, the 1/2 comes down. We have x to the power of 1/2 minus 1, which is negative 1/2. And now we take the derivative of that for f double prime. The derivative of 6x is 6, and then the derivative of 1/2 x to negative 1/2. The 1/2 waits outside, and we have negative 1/2 x to the power of something. Let's calculate what that thing is. Negative 1/2 minus 1, we're subtracting 1 from that power, so minus 1 over 2 minus 2 over 2. We can subtract the numerators now, negative 3 over 2, so that's our new power. And we really should clean this up. 1/2 times negative 1/2 is negative 1 over 4, top times top, bottom times bottom. And I'll say that's a good answer. Or sometimes you have to do this. 6 minus 1 over 4 times x to the power of 3 over 2. They're both good. So I'd say that step is optional. Don't sweat it. It won't be a trick. It won't be like, you'll have 2 of them, you have to pick the one that's most simplified. There'll be the one that's circled there or the one that's not circled. You have to know what they're equivalent, but other than that, that's all there is. Okay, next example, we have lots of derivatives being requested and the introduction of a new notation. Let's start with the nice ones. Take the derivative of f prime, 6x to the 5 plus 4x to the 3 plus 2x plus 0. And I won't bother writing the plus 0. Now we'll do the second derivative. 30x to the 4 plus 12x squared plus 2. Now we'll do the third derivative. 120 x to the 3 plus 24x plus 0. Now we run into the new notation. f4 of x means f with 4 primes. 1, 2, 3, 4. Okay, that's the fourth derivative. The 3 will come down, multiplied by 120, we get 360, x to the 2 plus 24. The next one means fifth derivative. You can see it starts getting tedious to write the tick marks, 1, 2, 3, 4, 5, and that's why that bracket notation exists. $720x plus 0. Now we have derivative number 6. With 6 primes, $720, and now it's asking us for the 99th derivative. 99th derivative. So you really don't want to be writing 99 tick marks. How many times are we going to have to take the derivative? So I've already tired of drawing tick marks. I'm not going to draw 7 of them. I'm just going to say 7th derivative. What is the derivative of 720? That's 0. Let's take the 8th derivative. What is the derivative of 0? 0 is a constant, so its derivative is 0. How about the 9th derivative? 0 is a constant, its derivative is 0. This is going to continue forever. The 99th derivative is going to be 0 as well. I got a question for you. You can answer it in the forums. I'll put a few questions. What is the nth derivative? Find the nth derivative of a function if f of x is a times x to the power of n minus 1. So if, let's say, n was 3, then f of x would be a times x to the power of 2. Find the third derivative. What is that going to be? Part 2, find the nth derivative if f of x is a times x to the power of n. Part 3, find the nth derivative of x if f of x is a times x to the m for m larger than n. And I'll do the last one. So solution for 3. So the first derivative, f of x is a times x to the m, and f prime of x is, the m will come down, so a m x to the power of m minus 1. Take the second derivative, we'll have a m times m minus 1 times x to the power of m minus 2. The third derivative, we'll have a m minus 1 m minus 2 x to the power of m minus 3. So then the power keeps coming down. It keeps getting reduced by 1, and it keeps going. Put a 4 here. A times m minus 1 times m minus 2 times m minus 3 times x to the power of m minus 4. What's going to happen if you change this number here? You'll change that number there, and you'll change how many of them there are, how many pieces there are. So here you have 1, 2, 3, 4 pieces. If you went up to number 6, you'd have a times m, n minus 1, n minus 2, n minus 3, n minus 4, n minus 5. the power of n minus 5. N minus 5. Sorry, n minus 6. Let me see. And you'll see questions that are very similar to this if you continue on to Calculus 1301 or 1501, which is a follow-up calculus, or which are follow-up calculus courses for Calculus 1000. And you may even see some inside quizzes and maybe tests or exams for this course as challenge questions. And if you do see them, you'll get fair warning. You'll get, for example, you'll be told, here's a practice quiz. Make sure you do this before your test. Okay, next examples where things get more interesting. We're asked to find the second derivative of an expression whose first derivative requires us to use the chain rule. So I'm going to take the first derivative. The chain rule, this is w to the power of 7. So 7w to the 6 times w prime when we take the derivative. We'll have 7 times x squared plus 9 to the power of 6 multiplied by the derivative of the inside. Derivative of x squared is 2x. Derivative of 9 is 0, so 2x plus 0, I'll just put 2x. We gotta be careful. Certain terms can be combined and certain terms cannot be combined. We cannot take that 7 and bring it into the bracket with a power 6 on it, because the 7 does not have a power 6. You can only combine brackets that have the same power, pieces that have the same power. The 7 and the 2x contain the same power. They're both raised to the power of 1, so I can combine those together. This is still f prime. It's x squared plus 9 to the power of 6 multiplied by 14x. And I'll drop the square brackets now. Okay, now for the second derivative. Before you start writing stuff down, think, what type of derivative is this? What rule do we need? And it's a product rule. We have an A. We have a B. So we're going to have A times B prime plus B times A prime. So B is 14x. Sorry, that's A. Oh, sorry, A. X squared plus 9 power 6. And then B prime, I'll leave a space. Plus B is 14x times A prime, I'll leave a big space. So A is x squared plus 9 to the power of 6. We're going to take the derivative of that using the chain rule. Six times x squared plus 9 to the power of 5 times the derivative of the inside, which is 2x. So I'll plop that in right there. 6 times x squared plus 9 to the power of 5 times 2x. And then b is equal to 14x. So b prime is just 14. I'll plop that in right there. Now I'll put it in standard form. We have 14 times x squared plus 9 to the power of 6 plus, we can take all the pieces that are off on their own. I'll do it in 2 steps though. 14x times 12x, the 6 and the 2x can multiply together, times x squared plus 9 to the power of 5. And I'd say that's a pretty good answer. I'll do one more thing underneath. If you're checking your answers in the back of the book, you'll see that they always do the next type of a step. They do as much common factoring as they can. So they take a 14 out, and they take an x squared plus 9 to the power of 5 out. And what are they left with? The first term has an x squared plus 9 left. The second term, we took the 14 out. We didn't take the x out. The x will go with the 12x. We get 12x squared. And then they can simplify. 14 times x squared plus 9 to the power 5. And then x squared plus 12x squared, 13x squared plus 9. But I'll say, please do not do this. This is what computers do. This is not what people should be doing. At least if you don't have a reason to do it. All you were asked for was for the derivative. The reason you would potentially think about doing a step like this would be to set the expression equal to 0 and solve for x. Something we'll do later, and we certainly wouldn't do it with this function. Not least of all because it would have no solution. This function is never equal to 0. It's always positive. Everything, all the x's are being squared. Nothing's being subtracted. Okay, another example, same type of strategy, but we'll hold off on that. This video is long enough. We'll do it in the next video.